Okay. All right, here's a question now. What if we got, like yesterday or the day before, we were talking about U substitutions, right? Okay. Here's another example where we could make this problem much, much easier. We could do this one without. We could expand out this binomial, distribute the x all the way through, and get a bunch of terms. Each of them we could integrate separately, and we get, it'd just be a pain. We could do that. But by making a judicious U substitution here, we can make it much easier. What is U going to be? That sounds like I'm using background.
Is this recording?
Yes, it is. Okay, so then what is du? 2x. Okay, so now let's make our, hey, yahoos, let's make our substitution then for u's, right? So we've got an x squared plus 1 right there. That's good. That's going to become a u. But we've only got an x dx. So what's that going to be? Yeah, it's going to be a 1/2 du, right? So when we make our substitutions, then this stuff gets to be a 1/2 du, and the 1/2 we might as well just pull out front because it's constant. Any constants, constant multipliers, constant factors. Works out well. This is when we substitute, we immediately get a complete substitution that helps us, which is what we want. Now, why does it help us so much? I think it helps to. I think it's good to look at why this works, so you can kind of get a feel for some intuition about which ones work and which ones don't. Now, what's the problem? And really, Lane, put that. Yeah, I want you to. You got to focus on this. I want you to tell me what's the part of this problem that was bad, that was problematic for us. What made this difficult in the first place? This integral, what made it difficult to do? Okay, say it again. The x in the front's not so bad. The x in the front's okay. If this were just x times, say, x squared, or x to the 7th, or x to the 9th, I could have combined those really easily. What's the part of this that would be a pain to have to deal with? The cube. Well, okay, the fact that the cube, what's being cubed, is a sum of two terms, right? So it's really the fact that it's x squared plus 1 that's being cubed that's the problem. So we'd have to expand that all out, right? And so we want to pick the u substitution that's going to make that problem area disappear. We want whatever's being cubed in this situation to be one thing instead of a sum of two things, which is what we accomplished. When we let u equal x squared plus 1, we took two things and made it one, and it makes life easier for us. When we make our substitution then, we end up with, our u cubed, right? And then this part you told me became a 1/2 du, right? But what's the one part that we haven't accounted for in that definite integral? Definite meaning it's got limits. We don't write it, but what's implied is that these are x values, right? If we were to graph this thing, we're looking for the area under this curve between x equals 0 and x equals 1. Now, it's not going to make sense for us to have x values in this integral, is it? Right? We got to transition to u values. That's easy to do, though, because we've got a built-in equation that relates u and x. All I have to do when I make a u substitution, I just need to know what are the new u values that go with these x limits by plugging in those x values to find the corresponding u values, right? So from this equation up here, when x equals 0, u would equal, 1, right? So we've got the lower limit u equals 1. Now what about when, let's do that. When x equals 1, what is u? 2. Good, so then the upper limit would just be u equals 2, right? And this is an easy one to do, is what is that antiderivative? The antiderivative of u cubed.
3 squared.
Not square.
U to the fourth.
U to the fourth. Oh, over 4. There we go. Right? And that's going to be evaluated from 1 to 2. And so why not just pull the constant out front and make that 1/8 u to the fourth from 1 to 2? No, but we changed. See, when x was going from 0 to 1, when x is 0, u is 1, right? So the 0 becomes a 1 when we flip to u's. When x is 1, u is 2.
Okay. So u is 1 also.
So 2 to the fourth over 1 over 1 to the fourth.
So it's, right, so exactly. So we got this 1/8 then out front, which we chose to pull out front, just makes less computation. And then we get 2 to the fourth, which is what? 16. Minus 1 to the fourth. So I get 15 times 1/8, which is 15/8. Yeah, how about that? Okay, now I want to show you something. Now this to me is what takes this to a whole different level. This is interesting. Watch this and be amazed. Okay, if I pull out, here's what I want to do. Okay. Okay, let's look at these two curves that we started with. Right, we got to scoot up a little bit, I guess. So, where'd that go? Darn it. Right there. Okay, so the first one, let's make it black. For the black curve, we had the function x times the quantity x squared plus 1 to the cubed, to the third. Okay, so let's graph this. If I hit enter, there it is. Now we're only looking at this between 0 and 1, right? I'm going to go ahead and make the limits go from, how about -1 to +3, let's, or 2, I'm going to do 2.5. Okay, and I'm going to do, let's see, we're going from, I'm going to go from -4 to +15. How about that? Okay, so now let's add up that area. Right, between 0 and 1, I can calculate a numerical integral. Lower limit is 0, upper limit is 1. Calculate, and there it is.
15/8.
And it's 15/8, 1.875. Okay? 1 7/8. Okay. Now watch what happens if I go down. I want to make this one blue. Do it in the same window. If I put in the other function. So I got to scoot down a little bit now. There it is. You have to just see this visually to appreciate it. Okay, so we got the blue function, u cubed, right? Well, we're going to call it x because that's our variable. So that's really a u, right? There it is. And we're going to go between 1 and 2 this time. So we're going to do the limits of integration, do numerical integral for that guy from 1 to 2. Calculate. There's the blue area. Well, hang on. Oh, I have got the 1/2 out front. Whoops. Darn it. Cancel. Go away.
You just have to change it.
Is that all I have to do? You think? 0.5 times.
So that's a plus.
Oh, whoops. Sheesh. Times. There it is. Oh, beauty. Okay. So now if we look at that integral, how come that went away though? Oh, darn it. We got to calculate it again. That guy from 1 to 2. calculate. There it is. What do you notice?
It is the exact same.
It's the exact same. But look at the graphs we created. Let's get rid of this garbage. Look at the graphs we created. They're different shapes, right? They're completely different shapes. This is huge. I mean, this is what allows us to make calculations in string theory. The fact that we can make a change, we can take two equivalent functions that look different, that are topologically dissimilar, and pick the one that's easiest to work with. Right? I've got these two. I've got this. Actually, I kind of said that backwards. They're topologically similar, but they're different graphs. But that's neither here nor there. We got this black graph that's a little bit more complicated to deal with than this really straightforward blue graph, which is just an x cubed, right? The limits have shifted a little bit, but it doesn't matter because the areas are the same, right? Did we need to shift back in this? Now let's compare this to what we did yesterday, because keep that out. Hold that picture in your brain. If we go back to the notes from, well, I don't know if I have the notes right up here from yesterday, but if we go back to the concept we did yesterday, now we would have had to go one step further with this from yesterday, right? We would have gotten our answer. If we did the same problem, and it were an indefinite integral, or an antiderivative, this answer would have been, instead of taking an answer over limits of integration, we would have had this plus c out there, right? And then we would have had to go back. So we would have gotten the answer from, if we were just trying to get the answer to a definite integral, we would have gotten the answer 1/8 u to the, what was it, u to the 4th plus c. And then we would have reversed the substitution. Right? We would have plugged in our value of u, which is x squared plus 1, and gotten the answer 1/8 times the quantity x squared plus 1 to the 4th plus c, right? And only then would we be done with the problem. This would not have been done, right? We wanted the answer in terms of x. What's the difference between that and what we did today? How come we didn't have to go back to x's in this case? And this goes to the very nature of a definite integral as compared to an indefinite integral. When we do problems that are indefinite integrals or antiderivatives, we get back a family of curves, right, that differ by a constant. Each differs by a constant. But the answer is going to be a function, right? In this case, it's that weird group of functions right there. Okay? When we do a definite integral, it's completely different. A definite integral has a definite answer. That's why they call it a definite integral, because it's an area. We're looking for an area under a curve. And the answer was exactly 15/8. End of story.
So that function, that's like a function of an area.
Right, this is an area function, but we're evaluating the area function over specific parameters, and so we get back a precise answer. There's only one area that's correct, the area under the curve. So does it matter if we're calculating that area in u space or in x space? Makes no difference. We just want the area, right? So there's no reason for us to ever have to go back, switch back to x's when we're doing a problem that involves limits of integration, because we're looking for an area, right? So in a way, those are actually easier. You don't have to reverse the substitution there, right? Okay, let's try one more of those. Okay, there was a good example. Well, that's right there. Okay, what about that one? Okay, what's going to be the u substitution here? 2x minus 1. And there's a reason for that. The reason for that is because I can easily simplify something like this. If I have say I have 2x squared plus x minus 3, all divided by the square root of a single thing. That's easy to do, right? Because I can think of that as being 2x squared plus x to the 1 minus 3 divided by x to the 1/2. And then I can split that into 3 separate fractions. Agreed? And so that's just going to look like 2x squared over x to the 1/2 plus x to the 1 over x to the 1/2 minus 3 over x to the 1/2, right? And this one is just going to become, what's x to the 2 divided by x to the 1/2? If I divide like bases, I just subtract, right? So
next to the 1 is 1/2.
Yeah, so 3/2 plus x to the 1/2 minus what? Minus
3 to the 1/2.
3 to the x to the negative 1/2. And then I could easily integrate that, right? No big deal. Okay. But now compare that to a case like we've got here. Even with just one term on the top, I'm stuck, right? Because if I have, say, x squared plus x divided by the square root of x plus 3, what can I do? I've got more than one thing in that radical, and so that's not going to be a like base with those, is it? Right? The difference being that on the top, if things are added, it's fine. I can split them up into separate fractions, but on the bottom, I don't have that luxury, right? So now, does that make sense now why your intuition is good? This is what we want for our u, because that's the complicated part. What's inside the radical is the part that's going to mess us up if it's complicated. Okay, so u equals 2x minus 1. So du just equals 2 dx, right? Okay, so if we make our substitution then, we get on the bottom, we've just got a square root of u, so that's just a u to the 1/2, right? And then we've got this dx. What's dx in terms of du? If I solve this equation, if I isolate the dx, which is what we have, 1/2 du, everybody see that? Just divide both sides by 2. So I get my 1/2 du. But what happened? Yeah, there's an x. Okay, so what do? The substitution is not complete yet. Okay.
There we go.
We go up there, and if we isolate the x, I get x equals what?
1/2, maybe 3/2 u. Right?
No, hang on.
Never mind.
U plus 1
over 2.
over 2,
Yeah.
right? So I can plug that in for the x, and I got it. Then I've got u to the 1/2, whoops, du, and then this x becomes a 1/2 I'll pull out from the other 1/2 and make it a 1/4. And then I've just got a u plus 1. Now look what we did. This is now, and I want you to see the subtlety of this. This is really, if you can get this, you can become a really good calculus student. You can start to see, and this is what separates the mediocre from the very good math students. What's that?
Caterpillars.
Exactly. Is if you could start to see the subtle parts of this, then you're set up to do big things in math. Notice what we did then is we took that sum of two terms in a very inconvenient place inside the radical, and we shifted it to a sum of terms in a place where it doesn't matter, on the top of the fraction. Big deal. We can split it into more than one fraction easily, right? So that plus sign, ultimately it's the plus sign, or the minus sign, plus a negative. That's the part that was problematic, and we just changed its location. Okay? All right, so then, now the limits, though. We've got to deal with the limits. So the limits used to be x equals 1 to x equals 5. If I go up to my key, this is the key that relates x to u. When x is 1, what is u? 1. Sure. Okay, so the bottom limit, the lower limit, is u equals 1. What about the upper limit? 9. So we're just going from 1 to 9, and that's a pretty easy problem now, isn't it? We can split that thing up into two separate parts. So that if I split this up, I'm going to get u divided by u to the 1/2 is u to the 1/2, right? Plus 1 over u to the 1/2 is u to the minus 1/2. Right? Okay? And we can just integrate that term by term. Should I slow down there?
Yeah, can you go over that?
Sure. So what we did, here's the plus sign. Here's the plus sign. Talk about that for just a second while I answer this phone. Eric, go ahead. Hey, Becky. No, I don't. I can check my emails maybe. Can I do that between? You need it right now? Okay, between classes I'll look. Okay, bye. Okay, does that make sense? So here's the plus sign. So if I split that into two separate fractions, I get u over u to the 1/2 plus 1 over u to the 1/2.
Yeah.
U to the 1 over u to the 1/2. Whoops. U to the 1 over u to the 1/2 is u to the 1/2.
Can you back up for a second?
Sure.
I'm confused where you got them.
The one from right there.
The 1/4. Oh.
Oh, the 1/4. Oh, that's okay. Yeah, that's right here. All I did was I combined that 2. When I substituted that x in there,
Okay, got it, yes.
that 2 came out with that 2. Okay? Does that make sense?
Yeah, I was curious where it came
That's where it came from. And then what I'm left with, when the 2 goes out front, then now I'm just left with the u plus 1 inside the image. Okay? Okay, so, and then 1 over u to the 1/2 is the same thing as u to the minus 1/2, right? And then integrating that then is, I can just take this term by term. So I've got the 1/4, we'll just leave alone. What's the antiderivative of u to the 1/2? U to the 3/2 over 3/2, which we could better think of as times 2/3, right? Instead of dividing by 3/2, multiply by 2/3. So this part right here is going to become 2/3 u to the 3/2, right?
Okay.
And then this part, okay, because we're just using our power rule. The antiderivative of u to the n is u to the n plus 1.
Oh, we're doing antiderivative. I keep
Right.
thinking we're doing derivative. Okay. Actually, I can do
Now what about this one?
negative 2/3 u to the negative 3/3?
No.
1/2
Over 1/2, which means times 2. Right? Okay, evaluated from 1 to 9. So we can put, yes,
I didn't get.
you're right, but what's negative 1/2 plus 1? Right? Okay. So now if we evaluate this thing from 9 to 1, we just get 1/4 times this whole thing at 9. Okay, well, what's 9 to the 3/2? 3/2 just means 9 to the 1/2 cubed. What's 9 to the 1/2? 3. Square root of 9, right? 3 cubed is 27. So 2/3 times 27 plus 2u to the 1/2. That's just 2 times 3. Right? Minus this whole thing at 1. If anything, u to the 1 is just, or excuse me, 1 to the 3/2 is just 1. Right? So I'm going to get 2/3 times 1 plus 2 times 1 to the 1/2 is also 1.
What is 2/3 to the 27?
It's 2/3 times 27.
Okay, I just said that down.
Does that make sense? Because that's what we get when I plug 9 in.
Yeah.
There.
3/2 27.
Yep. Okay. And then I'm taking 1/4 times that whole thing when we're done. Okay. Now I got to go next page.
False.
I smell you.
Okay, so let's do the algebra. So 2/3 times, so 3 and 27 reduces to 1 and 9, right? So that's going to give me 18. 18 plus 6 minus 2/3 plus 2. So 18 plus 6 is 24 minus, what is that, 8/3? is 72/3. 72/3 minus 8/3 would be 64/3. So 4 goes into 60. Well, I can reduce that a little bit. 2 and 32. So now multiplying straight across, I get 32 on the top and 6 on the bottom. 32, 6. Okay. Assuming we did everything right there on that side. I don't. Oh yeah, we could do. Sure. Yep. 16/3. Good. Yep. Okay. Good. All right. Well, is there anything else we gotta do here? Oh, I know one thing I want to show you. It doesn't really come up in the book. I'm going to show you one of the things. Okay, what if, okay, here's the question. What if I want to know, we said yesterday, we'll take a kinematic example. We said that the area under a velocity time graph gives you displacement, right? So if I do something like this, let's say I'm starting at the starting line at 0, starting at rest, and I'm going to pick up speed and start running, and then I'm going to slow down and come to a rest. And I want to know how far I went. Okay. That would look, if I looked at the graph of that, it would look like this. Oh. Right, this is velocity. And this is time. So that might look like this. Everybody agree?
Yeah.
I'm going to uniformly accelerate and then uniformly decelerate down to 0. Okay, and the area under that graph tells me displacement. Okay. And that's easy, 1/2 base times height, right? Okay, but now what's going to happen here? What's going to happen if I run out? Say I walk out here, and then I bounce off the wall and walk backwards to here and stop. Okay. Yeah. So what's going to happen in that case? What's that curve going to look like? Okay. If I'm walking at constant, this is physically impossible to do, but I'm a pretty remarkable person.
Without slowing down the constant rate bouncing?
Yes.
I'm feeling it's going to be yes here.
Okay, so that would look like this. I'm walking out there at constant speed, right? Constant velocity. I bounce off the wall, and all of a sudden, I go to there. Stop. Right? So my speed, yeah, it is.
How do you know?
How do I know?
Yeah.
Because that would imply infinite acceleration, which would turn me into
Obliterants.
yeah, obliterate. Yeah. Right. That'd be quantum foam. So what does that tell me about my displacement then? If I look at this area right here compared to this area right here, what do you notice?
Straight down.
That they are equal because I ended up right where I started, right? And so let's just say hypothetically that I walked at 2 meters per second for 5 seconds. So this is 5. Then that's 10, isn't it? That's 2, and this is negative 2, that's 10, and that's negative 10, and the sum of the two is 0.
Yeah.
Which makes sense because my eventual displacement is 0. I came right back to where I started. Okay, but what if? Now, what if that's not what I want to know? Because sometimes I don't want to know displacement. What if I want to know how far I walked? How could I figure that out? See the dilemma.
Say that again?
What if I want to know the total distance that I walked and not my total displacement?
It'd be,
Can you tell me what it was? No? Well, 20 is a number that might be important in our calculation. How far did I walk before I turned around, before I bounced?
5.
The 5 seconds.
Wait, 2 meters.
Wait,
per
can you,
second.
what was the,
So
what
this
was
is
the rate again?
2.
2 meters per second or 5 seconds.
Right, is how far?
So you walk 10 meters.
Oh, sorry. I'm sorry. Lane, you were right. I was multiplying 2 times 10. You're right. So it's 20, right? Because I walked 10 meters out here and I walked 10 meters back. Now the areas under both those curves, the absolute values of those areas are 10, right? And so what I can do here then, here's a strategy. If I want to calculate the total distance traveled, or the total area, that we might call it the gross area under a curve instead of the net area under a curve. The net area was 0, positive 10 plus negative 10. But the gross area, irrespective of sign, was 20. If I consider all the area to be positive, it was 20, right? So here's how you can do this. Every 0 of the function is going to divide it up into an interval. And then for each of those intervals that are separated by the x-intercepts, I'm going to calculate the absolute value of the definite interval, right? So I would cut the function between there and there, right? Find this area, take its absolute value. Between there and there, find this integral and take its absolute value. Does that make sense? Okay, so now for something that's a little less square, what if we did something like this instead? How about if we take, how about if we want to find the total area under f of x equals, let's see, I gotta think here. What if I wanted to find that? Total area under the function f of x equals x squared minus 3x plus 2 on the interval from 0 to 4, where all areas considered positive. So not the net area, but the gross area. Okay? So one thing I've got to do is I've got to find the x-intercepts, right? I've got to find out where this thing crosses the x-axis. So if I set the function equal to 0 and solve, what do I get? Is that factor?
Yeah.
Yeah. What are 2 numbers that multiply to positive 2 and add to negative 3? There you go. Oops. And so therefore the zeros are 1 or 2, right? And so if I actually look at the graph of this thing, what I'm going to see, my x-intercepts are at 1 and 2, and it starts off being positive, right? So my function's going to probably do something like this, right? Something like that. I'm going to get this little bit of negative area there that's going to throw off my calculation. If I just take an integral, I've got to calculate that as being positive, right? So I'd have to split this up then into 3 separate areas. I've got those 2, and then that 1, right? And so what I really have to do, if I want to write this all out, then I'm just going to call it f of x instead of rewriting the whole thing. My area would look like this, then it'd be the absolute value of the integral of f of x dx from 0 to 1 plus the absolute value of the integral of f of x dx from 1 to 2, see, plus the absolute value of the integral of f of x dx from 2 to 4.
What happened?
Because 2 to 3, we're under the same piece of area. We only have to split it where the function crosses the x-axis, right? Now, why can't I just, wouldn't it be easier to take the absolute value of the whole thing? Why, is that equal to, here's my question, is that equal to the absolute value of f of x dx from 0 to 4?
No, it's not.
It's not, is it? Because if I calculate this whole integral, there's going to be some subtraction going on, right? So it looks like I'm just going to get a positive answer and take the absolute value and get a positive answer. That's wrong. I have to take the individual pieces, the absolute values of the individual pieces, if I want to make it all contribute, right?
So we were getting the area under the curve.
So our goal here was to add up the total amount of area regardless of sign. So like if I were going to, let's say I wanted to, well, that kind of a bad example, but if I wanted to know very precisely how much paint I would have to paint all those areas under the curve.
But that area is not under the curve.
Well, but it's under a negative curve. When I say under the curve, I mean between the curve and the x-axis.
Oh.
So this is area I would also have to paint, so I have to account for it. All right? If I want to get the exact molecular amount of paint that I need to exactly cover that, then I've got to account for all the area that I'm painting. Okay? All right.